would like to acknowledge our sponsors, the Research, Discovery, and Innovation Group from the University of Arizona, of course, is one of our major sponsors, as well as TEP. On the next slide, also I'd like to, as Joaquin has pointed out many times, we have a number of very important sponsors. Today I just want to point out one, Visit Tucson. Brent Dorad's actually in the audience. He's head of Visit Tucson, and he's been a really strong partner for the community, obviously trying to bring people to the University of Arizona, to Tucson as well as the University of Arizona, and we've partnered really well with them. Most of you, the fact that you're here, know that Tucson's a science city, and this year, as you'll see, Visit Tucson has also acknowledged that Tucson is indeed a science city. So if you pick up the latest version of the Visit Tucson, which everybody who comes to the airport will pick up, it actually highlights the science that's going on in the city, from the Biosphere 2 to the Sky Center to the Mirror Lab here on campus, as well as the Tree Ring Lab, and finally Tumac Hill. Tumac Hill is, many of you have probably walked up and down Tumac Hill. It's been kind of a cultural center in Tucson for over 4,000 years, and the science there has been happening continuously for over 115 years when it was first started by the Carnegie Institute and has now been taken over by the University of Arizona. And as Joaquin has mentioned, it's been perhaps known as the birthplace of the whole field of ecology. But Tucson right now, Tumac Hill right now, there's a road that if you've been walking up, it's been cracked and a little bit disheveled at times. It's being repaved right now to improve access both for the research that's going on as well as the approximately 1,000 people who walk up and down. So in order to support that, we'd like to ask if this is of interest to you, both in terms of its recreational as well as scientific merit, become a friend of Tumac Hill. I have one more announcement before I'll introduce our speaker, and that is that we will take a pause in the lecture series starting next week and hope to see everybody in 2 weeks. I have to get my notes here. Okay, so I'd like to now introduce our speaker, Joellen Russell. Let me read a few things about Joellen Russell. Joellen is the Thomas R. Brown Distinguished Chair of Integrative Science and Associate Professor in the Department of Geosciences. Her research uses global climate and Earth system models to simulate the climate and carbon cycle of the past, the present, and the future, and develops observationally based metrics to evaluate these simulations. And she'll talk about the importance of those, especially in this rapidly changing climate that we live in. Joellen is the head for the modeling team of the Southern Ocean Carbon and Climate Observations and Modeling Program, quite a mouthful, SOCOM. And she currently serves as a member of the NOAA Science Advisory Board's Climate Working Group as an objective leader for the scientific community on Antarctic research, Antarctic Climate 21, and on the World Climate Research Program's Southern Ocean Panel. She is one of only 14 scientists behind an amicus curiae brief supporting the plaintiff in the historic 2007 U.S. Supreme Court decision on carbon dioxide emissions and climate change. Before joining the University of Arizona, Dr. Russell was a research scientist at Princeton University and the National Ocean and Atmospheric Administration's Geophysical Fluid Dynamics Laboratory. This is really a mouthful for me. I'm a physicist. She received her bachelor's in environmental geoscience from Harvard and her PhD in oceanography from the Scripps Institute at the University of California, San Diego. And as you can tell, she's basically a rock star. She's my personal rock star because she has also mentored my daughter in her science fair project. I do want to say that Joellen's work has benefited from the strength of the sciences at the University of Arizona, since her work utilizes and integrates many of the strengths of the university, such as planetary exploration, geosciences, and physics. And just like Ferial's lecture from last week and Donata's next week, Joellen strives to create certainty from things that we can't see. So please welcome Joellen Russell.
Thanks, Elliot. Ahoy, Tucson! permission to come aboard. No, thank you for coming. I was a little worried it would just be me and Elliot and Bo. And so I'm very grateful we have an audience. And a little shout out to everybody who's streaming. I know that you're gonna laugh, but there are viewing parties in places like Montana, the UK, and New Zealand watching us right now, so hey! We get by with a little help from our friends. Yes, absolutely. And I want to just take us from Fariel's amazing lecture on trying to see black holes, see dark things that can't be seen because there's no visible light. I want to bring you back home. I want you to come back here. This is us. This is our home. To quote Carl Sagan, everyone you've ever loved lives here. And it's blue. It's the most beautiful blue planet that we've ever seen. We haven't found another blue planet yet. Many planets. It's lots of fun being here at the University of Arizona because you're on such an amazing team. I'm actually joint in planetary and applied math in the Institute of Data Science and hydrology and atmospheric sciences because they're all so amazing. and I like to poach their students because they're excellent. But our blue planet is really special. And I just want to talk about the ocean and what it does for every single person on planet Earth, all 7 billion of us. And I've been an oceanographer. I've wanted to be an oceanographer since I was about 12. I grew up in an Eskimo fishing village 31 miles above the Arctic Circle in a tiny little village that, and I was certain I knew what winds were like, and every time at breakup, I would watch the sea ice go, and I would think, wow, where does it go? And now I know, which is the coolest thing, and I've swum in every ocean, all of them. But the cool thing is that, the ocean hasn't killed me yet. I've spent about a year of my life at sea. Yes, sea is hard. Imagine a 300-foot ship, like the size of the football field, right? And you're chugging up the side of a wave. Chug. Yeah, up the side of a wave in a football field-sized ship and shush down the other side. It's like zero G. You're kind of hanging there for a little bit, and then you dig the prow into the next wave, and this mountain of water proceeds to fall on you and push you down into the water. On a good day, it's this little spritz on the deck, right? And on a bad day, it's a little bit blue, and on a terrible day, it's black. And I still have nightmares about this because black water over your head. Don't worry, I'll tell you. So let me go back here for just a second. What you've been watching behind me, I bet everybody's like, ooh, that's really pretty. Is that from satellites? It's really gorgeous. It's not. That's math. That's a model. That's the new model. That's this model. It's the new FV3. FV3 GFS is the new weather model. It is a climate model, and now the Weather Service is using it so that you know whether to bring an umbrella. No joke. This is what we're using. And everybody's like, well, I don't know about those climate models. Oh, they're probably terrible, right? Yeah. They're so good that they had a bake-off at the National Oceanic and Atmospheric Administration, NOAA. They had a bake-off 2 years ago in April, and they put the weather model up against the climate model. Guess who won? No, I love the Weather Service. I do, and the GFS has served us faithfully, but climate model is where it's at. You know what a climate model does that a weather model doesn't? It includes the ocean. We need the ocean because it holds so much heat and so much carbon that it's actually affecting our weather, which is why oceanography affects all of you. And here, why do we need to do it in a hurry? Because the ocean's not staying the same anymore. And the reason it's not staying the same is because of this amazing CO2 curve. It's actually carved on the wall of the National Academy of Science. They wouldn't let him in until he was almost 65, even though he started his record back in 1958. I feel this very personally because when I was a brand new grad student and I brought my brown bag lunch to Scripps and I was trying to find a place to sit and all the picnic tables were full, down at the beach, except for one where there was this old guy with white hair. And I thought, he has a brown bag. Well, sit down. And I did. And it was Dave. And Dave said, hey, who are you? And I said, I'm a new grad student. I'm going to do carbon work in the ocean. It's going to be awesome. And you know what he said to me? He's such a kind man. He said, I do a little carbon work myself. I miss him. He was amazing, but he left us this legacy. The red line, that's the South Pole. The black line, that's Mauna Loa, that's Hawaii. The atmosphere is telling us all the same thing, and the National Oceanic and Atmospheric Administration has measurements all over the world now making these same records. And what it tells us is that the CO2 is growing fast, and that the atmospheric warming associated with, so the sun shines in, it warms the surface, mostly the ocean, because that's 71% of the Earth's surface, and then when it tries to re-radiate that back out to space, it gets scattered by the CO2, which is a greenhouse gas. So of course, the more CO2 we put in, the more scattering there is. But where does all that heat go? It goes into the ocean. Global warming is not atmospheric warming. It is ocean warming. If you take nothing else away from today, global warming is ocean warming. All the blue here, the light blue and the dark blue, all of that, and this is time on the bottom from 1972 to 2012, all of that blue is the heat, the energy accumulation in the ocean. And if you can't see it in the cheap seats, the atmosphere, it's this pink thing down at the bottom, the little tiny one you can barely see. Yes, that's the accumulation in the atmosphere. It's between 2 and 3%. It's tiny. And that's why every year is not perfectly warming every year in the atmosphere, although lately, whoa, it's been pretty bad, hasn't it? Almost every year we've had a record warm atmosphere year, but every year is the record warmest in the ocean. I just want to point out that so for us, we would be a lot hotter here in Tucson if the ocean weren't taking up quite so much heat. So yay, ocean, for everybody who lives in a desert. But boo if you're a coral reef. No, really, look at this. In 2016 and in 2017, here are the bleached areas next to the Great Barrier Reef. And now, like the far north, 26% dead, the mid is 67, the central 6, and only 1% are dead in the south where it's a little cooler. The Great Barrier Reef's half gone. The last time I gave a talk in this audience 3 years ago, it was still here. It's going really fast. I told everybody then, it's actually what I said last time, was if you want to see the reef the way it was meant to be seen, go now. You missed it. There's still some reef left down in the south. But it's very sad, and it's going very quickly because the ocean is warming, and the warming caused the coral to bleach, and then they die. Okay, other things. Well, what if I told you that, that we're predicting that the sea level is going to rise once we warm at 1.5 degrees, that this is Norfolk. This is our biggest naval base, right? Biggest naval base, everybody knows, in Norfolk, Virginia. And here it is after 2 degrees warming, and here it is after 4 degrees warming. And the blue and the dark blue is underwater. If you knew the enemy was coming to take your biggest naval base, what would you do? What would you be willing to pay? What would you be willing to sacrifice? What would you be willing to do in your daily lives if you knew your biggest naval base was going to be underwater in 20 years? Well, it might not be 20, but it's something like 20. Let me tell you how we're predicting this. And I just want to say, there's only about 6,000, according to the American Geophysical Union, there's only about 6,000 PhD level oceanographers in the world. Out of 7 billion people, we have 6,000 oceanographers. And they have to go to sea, away from their families, on ships, for months at a time in order to get out there. And really, we don't have enough ships, and we don't have enough hands, and it's really not easy. When I was out on one of my early cruises, and I'm a little nuts, so just forgive me, I had to drop this expendable bathythermograph, an XBT, off the back deck. I was a young scientist. I didn't have a big job. I had a little job. It was my job to dump this sucker off the fantail, which just had this little chain across the back and nothing else. And I'm in the Southern Ocean. It's in the winter because it's, cool, so cool. And I looked out. I had my line on, I had my zoot suit on. I knew the first mate was on the winch, and I looked out and I said, it looks really bad. but it's my turn. Looks really bad. So I went anyway, and I got about halfway across the fantail, and this mountain of water just picked me up off my feet and started to shove me off the back of the ship. And accidentally, the first mate had given me a little too much line, and I was going to go right off the back because he'd given me all this line so that I could run. He kind of misjudged it, and I might have gone right over into the propeller, but my steel-toed boot got stuck in the chain. Where it hooks to the side, and so, the water went off, and shivering like this, I dumped it off the side like I was supposed to. Scripps oceanographers, you can't stop them. But some of the people I go to sea with just spent 4 weeks with no paycheck. These are the people that run our ships, that keep us safe, that do this amazing work, and they just spend 4 weeks without a paycheck. I just can't. So let me tell you what I know about these people, these oceanographers, these scientists that work at NOAA and had to put into shore because of the shutdown. Courage, integrity, and endurance. Courage to try things that no one has tried. Courage to go places no one has gone. Integrity, to do the best measurements, to report the wins and to report the losses, report when it breaks. Here I am, my hands are shaking, I'm on my last electrode, and I'm thinking, oh my God, if I break this, my advisor's gonna kill me. No, seriously. And then you report it. Yep, I broke it. That's it, no more of those. And my replicates, and how many and how good are they? I learned it from them. Courage to do amazing things, integrity to tell it like it is, even when it blows, even when it's awful, even when you didn't get it. And endurance, to try it again when you fail. And I'm hoping that they'll try it again even when they don't get a paycheck. But that's a lot to ask. And I'm afraid, because NOAA has an aging workforce. And about a third of them are going to age out in the next 10 years. They're eligible for retirement. And we just made them spend 35 days with no paycheck. I hope they're willing to stick in with us, don't you? 6,000 in out the whole world. Because I can't do my work without them, and that work is telling us what's going to happen next. And what's going to happen next is we're going to get much hotter, and we're going to get drier, unless we make some behavior changes. And that's a big deal. And how do we know this? It's climate models. And these climate models actually, we know how much, so what do you put in a climate model besides math? The size of the Earth, the rotation rate, the topography, meaning the outlines of the Earth, and how much water there is, and how much carbon. And then you run it, just like that. It's amazing. And so the climate models are just the physics, and then you can add the carbon with the biogeochemistry and the ecology, which is amazing. Phytoplankton, trees, grass. Not flowers and not ants yet. I'm really sorry, Anna, but soon, I promise. We're working on it. And this is how it's grown over time. Anna Dornhouse is going to give the last lecture, so you have to come back, when she does hers, because it's going to be amazing. And so we started out in the 60s. Kirk Bryan, I've actually had lunch with Kirk. He's very kind. He reviewed one of my very first papers. He's very nice. And Suki Manabe, who still reviews my papers and gives me a lot of grief. He's really good, and he's still working. It's amazing. And of course, Ron Stauffer of Manabe and Stauffer, one of the first most famous coupled climate model papers. Do you know Ron Stauffer is adjunct professor in the Geosciences department here at UA? Yeah, he'll be here next week for a month, actually helping my students and the rest of the university get up. Do you know what we're doing? We are the first university in the world to actually run the model simulations required for the IPCC report next time. So we're going to be in CMIP 6, thanks to Ron, who I stole from this magnificent history of climate modeling, except he's still working. Isn't it amazing? So, and this is what we use for supercomputing power. It's insane. We basically have been following Moore's law. Back from the this is the Geophysical Fluid Dynamics Laboratory's computers and what was required in order to run these. It's why it is expensive. It takes a lot of effort. Basically, teams of scientists working over generations, like building a cathedral. This is what it takes. It's 2 million lines of code, and all of it has to be done to the utmost standard. They're the Climate Modeling Center of Record for the United States and the world, and they do extraordinary work. I was lucky enough to work with them when we were prepping for the 2007 and 2013 reports before, well, 2007 is when I got here. So, and it's kind of amazing. But I just want to point out that we've been telling you the same thing for a long time. And here's Wally Broker. I'm sorry, we were having lunch and I had to get a picture because, you know, he was here across the street at the Dutch. So his first forecast, and remember, he coined the term global warming, Wally Broker did? Yeah, he did. And so in 1975, this was his prediction. And in the background is 5 different data sets showing what the atmospheric warming has been. There's the prediction. That's what it actually did. There was another prediction, many, but in 1980, from Jim Hansen from NASA. You might have heard of his amazing testimony to Congress in 1988. And again, you can see pretty much on the money. How about this one? This was 1990 and the first IPCC, Intergovernmental Panel on Climate Change Assessment. Again, on the nose. And here is 2007. Okay, we're still seeing the same thing. And remember, now we've added a stratosphere and deep ocean and biogeochemistry and all this crazy stuff, and we're still getting the same answer. And sea ice, and here it is from 2013. Oh, sorry, this is 2007. And I just want to point out that we basically have been telling you since 1988 or 75 that global warming has begun. It's here. It's already here. And it's past time. We're talking about certainty and uncertainty in this lecture series. And so my field is a great example. How much certainty do you need? More? Okay, we'll work on that. I've got stuff to show you. All right, so the United Nations Framework Conference, I want to show you how did we get into this. That is President H.W. Bush. Papa Bush got us into the UN framework on climate change. Yes, 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 for all of us, all of the Democrats and the independents in the audience who go, oh, those Republicans. I'm like, no, 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 no. It's only recently that that's changed. Normally, this is all of us together working on the science and the policy implications of that science. Really, it's important to remember this is us. American leadership is a tradition in science, and it's no less a tradition in climate science. So, you know, we just have to work together on this. All right, so in the IPCC history, and I'm just showing you the whole thing, there's been a whole lot of reports, and now these new, like the Paris Agreement, et cetera, and this global stocktake, which I am working hand over fist to get ready for, and I'm gonna tell you what we're doing in order to get ready. But here's just one little thing I wanna point out. In 1990, the report did not quantify the human contribution to global warming. So if you first started looking at climate change in 1990, you go, well, not much there. In 95, a discernible human influence. In 2001, likely. In 2007, very likely. In 2013, extremely likely. 95% chance responsible for more than half of the Earth's temperature increase. So you're forgiven if you made up your mind in 1990. But we've come a long way since then, and it's worth taking a look at. So what are we doing here? I want to talk about what the University of Arizona is doing. It's so exciting when a land-grant university with a wealth of science and humanities and fine arts get together and try and do something really big. It's exciting. So how are we reducing uncertainty here? So my mother says this horrible thing to me, which actually makes me run even faster. She says, we're running out of the burning building of the past into the dark night of the future, with only what we can carry with us. And our math, our science, our climate models are just trying to shine a little bit of light on the path in front of our feet. Just a little light. What wouldn't you give for a little more light? Just a little bit more certainty about what might happen next. What would you give? And I'll just show you some of the things we've been doing right here at UA. So we've been building better evaluation of our system models to try and reduce the uncertainties and get better models. And this is two parts, building better metrics and getting more scientists to look at it. So on the top here, this is the observational uncertainty, the 3 different kinds of observational data sets. And then this is the different climate models. And, this is the Chinese model. There's a NASA model, some from Japan, from France, from Canada, from Germany. And here are the GFDL models up here. They're very, very good. But we need metrics in order to figure out how good are they and can we improve them. So we make a whole bunch of these. Oh, and by the way, so we threw this hashtag Great Antarctic Climate Hack because I want to do the ocean around Antarctica because that's my favorite spot in all the world. And at first it was just going to be sort of a few people. And then they said, hey, can I come? And pretty soon we had t-shirts that made us look like NASCAR. I mean, really, seriously, the community bought in, and we had penguin guys said, hey, I've got tagged penguins that are going, they're being flung out of the gyre with this, the winds are blowing so fast, the currents are going so quick, they're getting pulled away from their feeding grounds. Can we use that? Yes, we can. How about sea ice? Yes, we can. How about algae in the ice? Yep, absolutely. Irradiance, snow depth? Absolutely, we can use all of it, and we did. They brought their own data sets, we brought all the climate model stuff, and we actually built metrics in real time. It was a lot of fun. So we grow the community using observations to evaluate climate, and then we do Antarctic and Southern Ocean metrics for ESM-Val tool, which is what we give to the climate modelers so everybody can use the same evaluation tools on any model. It's kind of an automated thing. And where do we host all this fabulousness? At UA, at Cyverse. Just by the way, Nirav Merchant has been helping me turn bits of Cyverse into iClimate, my favorite computing platform, for a long time. He's a genius. I'm so glad he's here at UA. He's one of my top 10 reasons never to leave, Seriously, look at this. It's not just that we're a land-grant university that's opened the doors to everybody and the public. It's that we're also opening the doors online. You can, anybody in the world can actually get an account and do an analysis right here on Cyverse. It's $100 million of National Science Foundation money that supports this unbelievable facility for making groundbreaking, everybody in the water breakthroughs. I am thrilled, and only at UA. There is no other facility like it in the world. It's extraordinary. And this is where we have built all these metrics that we've actually exported to the Earth System Model Evaluation Tool. We have a whole package of metrics. Did you know we have almost more than they have in El Nino? Because we opened it up to more people in the community. We got more help. Yes, I love it. And of course, now that we've gotten better metrics, now what we need are better observations. Sorry, this is another one of my favorite things. So, robot floats, doesn't that sound cool? It's even cooler than that. So, ship measurements. One, a ship costs about $50,000 a day, bare boat, to go one of the deep sea ships. So the problem is you can do 3 profiles from top to bottom every day because it takes 4 hours to get the winch all the way down and 4 hours back up. So you can only do 1, 2, 3 every 24 hours at best. So every 2 days it costs $100,000. That's why this is so sparse, why so much of our ocean is white. Because actually, after 1989 and the Cold War ended, they actually started mothballing ship after ship. They didn't replace them. So we actually have a diminished fleet. We make fewer measurements now than we did in 1990. I know. And it's, and the number of places you can go to get funding for oceanographic work has dwindled. It's basically the National Science Foundation and NOAA, and that's it. There isn't anywhere else to get money to actually go to sea or do these measurements. However, oceanographers are sneaky and awesome, and they built robot floats. Who did this? Look at all those measurements. Now, we still need ships because all of the really detailed, hard-nosed, climate quality measurements that we compare these to have to be made from boats. But I'm just going to give you a little snippet because my student, Becky Beedling, who's a grad student here, who's already published her first paper in the Journal of Climate. She is amazing. She's a Carson scholar. And she went to sea last summer and deployed a bunch of our floats. And I just want to show you, this is that old thing that has to go all the way down to the bottom and all the way back and takes a minimum of 8 hours to do it. And the reason it's so big and heavy and takes so long, and you're seeing it on a beautiful day, imagine doing this in bad weather, each one of those has to be sampled. They fill at certain depths by pressure. And it triggers the little thing, it fills the bottle, and then we bring it all up. It weighs about as much as a VW bus. It's very heavy. And then we have to do all this sampling. It's incredibly hard work, as you can see. But there's Becky deploying what is an Argo float, one of our SOCOM floats, into the ocean. Yeah, she muscles it right in. Look at that. UA students are amazing. But working at sea is difficult. And so we decided we wanted to do something with floats with carbon so that we could figure out how much carbon the ocean was taking up. So the Southern Ocean Carbon and Climate Observations and Modeling Program and my friend Jorge Sarmiento and I and some of our other colleagues got together and we put together a proposal for a science and technology center to put in these biogeochemical Argo floats and then assimilate all that data into models. And the first time we proposed it, the sequester happened. And we were funded, we were picked as one of the 5 new centers, and then they called us in July, July 3rd. Sound like, you know, sort of a coup in the middle of the night? It kind of was, because you couldn't exactly call them back and go, what? And they said, so 5 centers, but, you know, we've decided because of the sequester we don't have enough money, and yours is one of the ones that's not getting any money. Oh, I could hardly get out of bed in July. It was terrible. So what we did was we put in a white paper and said, I'm sorry, this is the most important thing you can do. We need you to do this. Here's all the math. Here's all the numbers. Here's what we've calculated. Each one of these floats will give us 250 profiles and will cost $100,000. Each 2 days of ship time gives us 6 profiles. 6 profiles versus 250 for the same money. We have to do this. And they came back and said, you're right. I know. It's amazing. And so we put them in the Southern Ocean. Everybody's like, why? Why not off California? Because, in fact, the Southern Ocean is where the deep water comes all the way up from the very deep, like 3,000 meters long, like 30 football fields down to the surface. And that water actually does something extraordinary. It takes up a profound amount of heat because it's so cold and it's mixing so quickly. So it accounts for about 2/3 to all of the ocean heat uptake goes in around Antarctica. So that's why we started there. You know, so why do you rob banks? Because that's where the money is. That's where the heat is. It also happens to be about half of the annual ocean uptake of carbon. Again, why do you rob banks? Because that's where all the carbon was, yes. And it happens to be the place where the nutrients, the plant food, was actually, the plant food that's upwelled from deep, where all the stuff, the poop and dead bodies have been rotting and turning back into fertilizer, it upwells there and then gets exported to fertilize the globe. It's so important. So last time I came to see you, I had a few little floats and then a projection of where they were going to go. This is where they went. I'm back to report to you that, in fact, we've deployed 126 floats. We're going to have 200 in the next 18 months, you know, by the end of our deployment plan. We're putting in a new proposal. They've encouraged us to put in a new one to go for another 5 years to look at what the decadal variability, like El Nino and other things, are having, and the big budgets over time and how they're changing. Just remember, this is Hannah Zanowski. She started out as a physics and math double major here at the University of Arizona, and she got her PhD from Princeton, and is now a working oceanographer at the University of Washington. I bet you didn't know we were so good at oceanography in the desert. We're really good. So, excuse me. These floats sit at 1,000 meters. Every 10 days, they drop to 2,000 meters and make a profile to the surface. At that surface, they beam their data back by Iridium satellite, and we post it with an automated algorithm QC, quality control, within 2 hours. And it's publicly available to the world. Absolutely transparently, you, the taxpayer, paid for all this research, so we don't bogart any of it. We let you have it all. You can have our algorithms, you can have our data, you can have our models, you can have our model simulations, and you can have the metrics we made to actually look at the model simulations. You don't really want it, but it's all available at iClimate, because we are into radical transparency. We believe that everybody should steal this book. Steal my book, steal my data visualization, help yourself, any of it. I have toolboxes. They're digital toolboxes. I have tool sheds full of toolboxes. You are welcome to all of them. Come on in, the water's fine. Check our work. We want you to. In fact, we're trying to get our friends to check our work. We're checking their work. We're trying to accelerate discovery, because that change in the heat uptake, that change in our climate, the fact that the Great Barrier Reef is half dead in 2 years is killing me. There's nothing I would rather do than look at my sweet kids are there in the audience, and I look at them and I see the possibility of grandchildren potentially sometime in the far future, and I think to myself, those grandbabies will not think for 1 second that their grandmother didn't go right to the mat for them, right? This is their future, their planet we're working for. So we'll deploy any float we have to deploy. We will, okay, I'll show you the other stuff we did too, because it gets worse. So here are some of the people I work with. Lynn Talley is one of the most famous oceanographers in the world, literally. She was my advisor when I was a graduate student, and now she's my colleague, and she's the lead for the observations on this SOCOM project, and I'm the lead for the modeling. And Ken is the one who actually invented the little pH sensor that lets us see the carbon uptake and the acidification. And Steve is the one who builds our floats. He's an amazing professor at the University of Washington. These are amazing stained glass window kind of people. I can't tell you how proud I am that I get to work with them. It's amazing. The fact that they put up with me is kind of amazing too. Because push, I'm in a hurry. Yes, that's right. So air-sea carbon fluxes from floats. All of our floats, Allison Gray was one of our postdocs, who's now a new professor at the University of Washington, found out that the ocean is actually degassing carbon a little bit in the winter, which is cutting how much the Southern Ocean is taking up. This is a little worrisome. It's something we're working on in the models right now, because we're worried that we may be pushing into a future where the ocean just can't take it up, not because it isn't soluble, but because the deep dead body water is coming to the surface preferentially and faster. And we're worried about it. And our floats are the first estimates in the winter ever, because nobody goes to sea in the Southern Ocean in the winter unless you're a really overeager grad student. And this is Allison and her amazing paper that just came out, and she's got this fantastic new job and she has 2 beautiful babies. They're so gorgeous. And here is Ariane and Matt, who actually took all our fabulous data and assimilated it into an ocean model. And Matt is actually working with my grad student, Stan Swarczyk, who is just built himself an ocean biogeochemistry assimilating ocean model testbed for the Argentine basin near Chile and Argentina. So proud, can't tell you. And let me show you what they do with that assimilation. Now, the float data, the actual observations, are in the little dots, and the model is in the background. And if the dot looks like a different color from the background, then the model's not as good as it should be. But if the dot and the model match, then bingo, we're on the right track, right? The model and the data are telling us the same thing. Yeah. And here, this is for the oxygen. You'll see we don't have as many floats. They're kind of popping in now. This is time. You can actually see 2014. So we're putting in more and more floats. And you can see they don't do quite as good a job because we never had any that measured oxygen before. This is it. This is the first ever. First ever. But we're trying to train our models to do it better, right? So we're testing it with even the pH. And notice there is no measurements. I actually can look at a map of all the pH measurements from ship and pick out my 3 or 4 cruises. Because I was making those measurements back in grad school and postdoc, and there just still aren't any. So hence floats, woohoo, look at them all. And you'll notice they aren't matching as well as we would like. So we're working on this. And here's the carbon itself. Again, this one we can't even animate because there just is so little data seasonally at all that we just had to average the whole year because there just wasn't any ship data. And here we have the floats kind of popping out where we have new data. This is it. This is a revolution in oceanography. It's a revolution in how we look at our planet. how we use Earth system science to understand where all the heat and where all the carbon have gone. Every molecule, every single one. We are looking after them all. Seriously. This is how we know what's going on our planet. It's how we forecast the weather now. It's how we actually do climate modeling and tell what might be coming next. And it affects everybody on planet Earth now. It's not just the Great Barrier Reef or the Norfolk Naval Base. It's how hot it gets for, you remember last September, we had a record hottest September ever in Tucson. And I thought if I can't put my kids out to play in the afternoon, I'm going to have to drink a lot more. No, sorry, that didn't come out right. Oh, that's awful. Sorry, Mom. But seriously, it affects all of us. It's really important. And we're also learning really amazing things. So this is one that Veronica Tamsin, who's now got a position in Australia at their CSIRO government lab, and she's actually leading deploying floats in Australia now. Can you believe it? We've spread out. What she did was, and I want to show you, this is kind of amazing. She was a student of Lynn Talley's, and a postdoc with Lynn Talley, excuse me. And this is actually in a model. Obviously, you can't do this with the real world, but it's actually, they sewed particle tracers into the water to see where the water came up around Antarctica. So you're seeing the big Antarctic circumpolar current, and those particle tracers spiraling to the surface. That's that deep water we're worried about with all that carbon in it. It's kind of amazing what we can do with both observations and fantastic models. And we have both. So we also want to do some experiments on the Southern Ocean because we felt like our models probably weren't. So basically all the climate models today, all of them use painted white rocks for Antarctica. No ice. I'm serious. It's just snow. You can snow on top of the rocks and then melt that, but it's just basically painted white rocks. There is no ice sheet. The ice sheet doesn't melt. Now, we all know that the ice is melting like crazy, so we did a perturbation experiment, and it's actually my postdoc, Ben Bronslayer. I stole him from Oxford and Cambridge. Can you believe it? And he did an amazing job with my colleagues at the Geophysical Fluid Dynamics Laboratory, where the Antarctic ice sheet has a huge amount of meltwater. It's 60 meters of global sea level rise on all of Antarctica. Now, not all of that's going to melt in a day, for sure, but a lot of it is threatened because all that, remember I told you all that upwelling water and all this heat, and it's kind of brushing up against this edge of Antarctica? Well, it gets underneath here where the grounding line is, and it heats it up, and it melts it. And what we're worried about is that the whole ice sheet is starting to slide towards the ocean because we've unmoored it from, it was kind of stuck, and now we've melted the doorstop, and now it's just kind of heading for the ocean, which is warmer, right? And it's going to melt. You know, like if you put an ice cube in a hot drink, that ice cube's going to go. It's going to go much faster than you just left it on the table. Okay, so when we melt all that water, no more white rocks. When we melt all that water and we put it in around Antarctica, and we run a whole bunch of simulations, like 30, say, because we're just, you know, because we have the resources, and it makes sense because we could get a different answer from a different run because there's a little chaos involved here in the weather. But what we found was that when we put in this extra ice melt in the perturbation, the heat is trapped in the ocean. It doesn't actually come out, which actually makes the surface a little cooler, which is good for us because then the atmospheric temperature doesn't warm as quickly. However, you know, you're all thinking about that Norfolk base, right? Because what's happening when you trap all the heat underneath here is it warms by about 6 degrees. It warms a lot because it's not degassing all that heat to the atmosphere. And when it doesn't degas the heat, it basically melts the ice sheet. And we're very worried. It's a feedback. The more fresh water melts, the more heat builds up. The more fresh water melts, the more heat builds up, etc. So what we found was it actually slows the rate of global warming. It means about 10 to 15 year longer grace period before we hit 2 degrees. That's big. That's 10 to 15 more years. Not enough, but we'll take it, right? However, it also meant at the same time, it moved the precipitation. We actually made it drier on the south side of the equator, so here's Australia burning up, and made it a little wetter on the north side, which might actually be good for Tucson. You know, we'd have to check it more, but it's not significant over Tucson, but we think it might be better, where we actually moved the entire intertropical convergence zone to the to the north side of the equator. And actually, everybody's been saying, but what about the sea ice? You can't predict all this growing sea ice. I'm like, actually, the climate models, when you put in the fresh water from the melting sea ice, predicted that the sea ice would grow because you made it cooler in the surface water. So yeah, check, check, check. It's exactly what we predicted, and it's what we see today. So we're pretty excited about this. And okay, excited because we're scientists and we love new things. Worried because we're people and we have friends who live in coastal areas. So what happens next? The subsurface warming is predicted to get even bigger in the ocean temperatures. Remember, by more than 4 times. We'll get increased freshwater warming focused at the coast, and that ice melt becomes a positive feedback. You will get even more melting because of that warming associated with the original melting. So positive feedback. And we checked it. The observed zone, here's the warming from our model. Here's the observed warming right up against the coast. And here's the warming from our floats. Okay, we made a hypothesis. We tested it in the models by putting in the fresh water. And then we checked it against our float data. Boom. I love this paper. And we have 2 more, one that's already out for review at Nature Geosciences. This one came out in Nature in December. It was very exciting. And just to remind you that these predictions were just from the expansion of water. It doesn't include any of the fresh water from Antarctica. This is new. So we're worried. Okay, what can we do about it? Let's talk Turkey. Trust but verify. I know I'm using an old Reagan slogan, but I really like it because I trust that my friends, I work with people all around the world, from where do we put to sea? From Cape Town, Dunedin, New Zealand, Australia. We put to sea in all these ports, and 2/3 of the floats that we've deployed were not deployed from US ships. They're deployed from bootleg cruises from the UK, from France, from Germany, from South Africa. We are an international program, and so as oceanographers, touching 71% of the world, and there's only 6,000 of us, you better believe we lock arms with our colleagues worldwide to get this work done. This is the bad part, is when you give a fancy Ivy League education to a girl from a get-her-done state, all kinds of trouble ensues. And then you put her in a big state like this one, and these are all the people who are involved in this amicus brief. I don't know if everybody knows, but in 2007, the Supreme Court ruled that the EPA is required under the Clean Air Act to regulate carbon dioxide. The Supreme Court ruled. And we filed an amicus brief, the 13 scientists, and said the science is solid. Because duh. Sorry, we didn't actually say that. But I really wanted to. But Scott Zaleska and Kirsten Engel, who's in the law school, et cetera, was the one who organized us, and Jonathan Overpeck, who's gone off to the University of Michigan. We helped put this together. This is a U of A-led project, really, seriously. And now it's actually required that it be regulated. And I have a lot of hope. I do. Everybody says, how can you have hope when look at this total, you looked at the total CO2. But here's the USA. We dropped 15% over the last 10 years since 2007, while growing our economy. We can do this. We can do this. We've forgotten what happened after World War II with the Marshall Plan. We've forgotten how hard we can work, how much we know. I say, you could take Churchill, who says, I offer you nothing but blood, sweat, and toil, except we can do this. We did it. We're doing it. Well, okay, except for last year. It increased last year. I'm very disappointed in all of you. No, seriously, this is all of us working together. It's fuel switching away from coal to natural gas. Hopefully, eventually, we'll go from natural gas to solar or nuclear or hydro. Oh, wait, those are things we do here in Arizona. Yes. Why aren't we the green state? Why can't we hang out our shingle and say, hey, steady, green, no carbon, no pollution power, and one of the most beautiful states in the country. Come on in. This is a case where sustainability and prosperity can absolutely align. They go together. And why can't we sell it to the rest of the world and help them save themselves too? You know, never a bad idea. All right, so the problem we have with verifying these agreements is that what we're doing now is bottom up and it's self-reported. This is never going to work. And top down, we still don't have enough measurements in the ocean. And the reason I'm saying that is I'm going to rearrange this equation. If I know the atmosphere in the ocean, and I already know the atmosphere really well, thanks to Dave Keeling and all of the work from NOAA, if I had enough floats in the ocean, then all of the rest of this is actually within national boundaries, which is only 28% of the Earth's surface after all, and the top 10 economies actually happen to be out of some of the biggest countries: Russia, Brazil, the US, China, you get the picture. So how many floats would it take for me to reduce the uncertainty in ocean carbon fluxes? And I'm actually doing this simulation. This is Matt Maslov did this, and it's amazing. How many floats would it take? And each one of these is covariance around it. So on land, you can imagine trying to put enough sensors to measure this, like in a forest with a Walmart, with a train running through it, and a coal-fired plant. How could you tell? I mean, you'd have to have like one every 5 meters or something. It'd be very hard. But in the ocean, actually, you can have one every, 200 miles and still get most of the variability. And so we started out just in the Southern Ocean, and this is what the global biogeochemical Argo looks like now. And you want to know when we had our planning meeting? January 2016. And it's 2019 now. After I gave this lecture, I went to this meeting in Villefranche, France, and 9 out of the 10 float deploying countries were there, and we made a plan, and we deployed the freaking floats. I know. And then we went to the UN, and right after our current president pushed the president of Montenegro for a photo op, they kicked us off. They kicked us off the International Oceanographic Commission. And I needed to get our sensors approved. It would have been nice. And then Japan proposed them for us, and 2 countries from Africa backed them up. And they're landlocked, and they did it anyway. And I was so proud and so pleased, and just so much faith in humans that we can do this, because that was amazing and kind and took some effort. And now it's actually in the Global Climate Observing System plan. Can you believe it? Check it out, right there. So we're trying to build the next generation carbon verification system, and I need one more thing. I need a lot more wind information over the ocean. So we put scatterometers up, and I know I'm almost done here, but I have one more cool thing to tell you about. So, I love supercomputers and robot floats, and we do that here, but one other thing we do here at Arizona? Space. So we put in a proposal with our friends at Ball Aerospace and BYU, who's the engineer, David Long, who actually built the last scatterometers for the United States. Scatterometer bounces a beam off the ocean, and if you have high waves, it diffuses the beam, and you get less back to the satellite where you detect it. And if it's flat and glassy, you get the whole beam. And actually, the wave equations work really, really well, thank goodness. And I'm going to talk about the wave equations in just a second. They were very important to United States history, and I bet you don't know why. But so we've actually proposed to NASA to put a smaller, the old ones cost $1 billion to $1.2 billion, which is ridiculous, and we only get 1 measurement a day in every spot. That's just not enough. I need more. And so David's come up with a concept that would be only about 100 million. I know. Positively cheap, I tell ya. And of course, it would be polar orbiting, giving me my southern ocean winds, as well as the 2 coasts of the United States, where we have a lot of deployed equipment as well. So we're working with Ball Aerospace. We put in this proposal, and I just want to point out that if I use hourly winds instead of the daily winds, what I get is a 44% different carbon flux. So I need those stinking satellites. I mean, not, So Zephyr is the name of it, and we're really hoping NASA says yes. And by the way, it'd be hosted right here at the University of Arizona. Yes, exactly. And I'm the science team lead and the deputy PI, and it would be hosted here. So I'm very excited about this. So 10 years ago, we didn't have an international political agreement to address the carbon cycle. We didn't have carbon-observing satellites. We didn't have our system models. And we didn't have biogeochemical Argo floats. Now we have absolutely all the pieces. There's no reason we couldn't build this verification system that could then allow us to basically send out kind of monthly bills to the top 10 economies saying, hey, great, good. Anybody have a nest with little leaves? You get a leaf. You did great. You over there, you get negative 10 black leaves. What were you thinking? Turn that coal back off. So we're really excited, but I want to tell you why. One of the things that moves me as fast as I can go. Walter Munk, and I've only met him a few times, but he was a professor at Scripps when I was there, and he's a geophysicist. And he was a young man during World War II, and he was working on the wave equations for the landings in North Africa. And he told his supervisor, sir, the gunnels on the boats can only handle waves of 5 feet. And if you go to 6 feet, then they turn into the waves, they swamp, and everybody drowns. And his supervisor said, you're just a kid, get out of my way. And so he called his advisor, Harold Fairdrop, who's a very famous oceanographer, and said, I can't get them to listen. And Harold dropped everything and went across the country to help him, and said, and together they did the wave equations, not just, but for D-Day as well. The story is that he was the last call that Eisenhower made before the D-Day landing was to this man, Walter Munk. And Walter stood at the Ocean Sciences meeting 3 years ago, and he said to this plenary crowd, like your size, basically half the oceanographers in all the world, and he said, Hitler was my generation's challenge. Climate change is yours. You must hold the line. We will come to reinforce you. You must hold. And we're trying. We are working at it. We will do everything we can. But when we have shutdowns, when we tell the taxpayers, we need another ship, we need more floats, it's not that much. We'll do the best we can with what we have. And we've given you as much certainty as we possibly can. The answer has not changed since 1975. But we need your help. We need your help. We're doing the best we can, but there's only 6,000 of us. But we are not less valiant than our grandparents. We are not less determined than our grandparents. We the same as those Noah folk who had to go to shore. Courage, integrity, endurance. We promise, we will get there. But we would love it if we could all go together. So please, we need to turn the ship now. Mayday, 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 now. Please, thank you.